Why? Because in the interview, they ask draw a TTD diagram, time temperature transformation diagram. They ask you guys to draw it and explain it. So you need to draw it and you need to explain. Like iron carbon phase diagram is important. Draw it and explain it. So they also ask sometimes show us TTD diagram and explain it, how it is happening and what is happening exactly. Because this concept actually helps you in heat treatment again. See, so the first topic is decomposition of austenite phase, right? And we till now we know that austenite is a parent phase, because most of the heat treatment is done from the austenitizing temperature, where we have a homogeneous austenite phase. Only grain and grain boundary of austenite. Nothing is there. Everything is in solution. So, what is the definition of austenite? Can anybody tell me? Who will take? Don't hide your face. Yeah. Can you tell me what is the austenite? I'm asking you. What is austenite phase? What it means? Yeah, sure. Can you tell me what is austenite phase? Can you define austenite? What is the definition of austenite? I'm asking. In simple words, you can say. There is no issue. Can you tell me what is the austenite phase? Satyajit, can you say what is the austenite? It is non-metallic. Austenite is why it is non-metallic. It is metallic, of course. Yeah, solid solution. Yeah, you are saying something. Solid solution. At least he is correct. It is simple definition is it is a solid solution. You are telling that is right. It is a solid solution of carbon in gamma iron or FCC iron. Whatever you can say, that is fine. Or you can say interstitial solid solution of carbon in gamma iron or FCC iron. Iron is FCC, but carbon is in interstitial sites, and it is forming one phase that is called austenite. Okay. It is a solid solution. Whenever there is a concept single phase means it is a solid solution always. Okay, fine. So see, so just imagine you have one eutectoid steel right now, and you are taking to the austenitizing temperature, and you are forming a homogeneous austenite. Now your option is what? You remember in heat treatment cycles we have 3 cycles: heating, holding, then cooling. Now you have austenite phase, that means you have started holding it, fine. Now you want to cool it. So depending upon the cooling rate, you can have these 3 kind of things: perlite product, or you can have benite, or you can have martensite. These are the 3 products you can easily get. Okay. But the point is how you can get perlite. This is important. Perlite will form from austenite by diffusion based. Diffusion need to happen only. Diffusion need to happen means, see, austenite is FCC face centered cubic. That means what? Atoms will be at the corner points and atoms will be at the face centered points. And carbon atoms will be at the interstitial sites. Which are the interstitial sites? Edge center, center edge, and body center. You remember, or shall I? Because I am quickly drawing it. Okay, so you have iron atom here. You have iron atom here. Iron atom, iron, and iron, right? And carbon atom will be where? It will be here, edge, small carbon atom in the edge, and at the center of the body. Like suppose the body center. So this is carbon, this is Fe. Okay. This is a simple unit cell. I'm talking about the unit cell. So this is the structure, right? But this arrangement will break down. The moment you cool the steel below A1, right? Because I am considering what? Eutectoid steel. Eutectoid steel means above A1 austenite is stable, but below A1 austenite is unstable. So So once you make the austenite unstable, it cannot remain as austenite. It will break down into either pearlite or benite or martensite. You got the point? So you need to make the austenite unstable. How it can be done? Just bring the steel below A1. But if it is hypoeutectoid steel, then you need to bring below A3, right? And for hypereutectoid steel, you need to bring below ACM. Okay, you got the point. Then it will become unstable and transformation will start. Okay, so this kind of transformation is called diffusion transformation. Diffusion transformation is also called reconstructive transformation. Reconstructive means all the atomic bonds will break down and they will again rearrange in a particular fashion. It will form Fe3C, which is a carbide. Carbide is having orthorhombic structure. Just imagine, you have this is FCC now. Austenite is FCC, and it will finally become what? Pearlite. Pearlite is Fe plus Fe3C, right? This is PCC and this is orthorhombic. Orthorhombic, right? So orthorhombic structure is different. BCC structure is different from the FCC. So how it will form? Where all the atomic bonds will break down and it will rearrange again. So it means your iron atom will also diffuse, it will move, and your carbon atom, which is present in interstitial site, will also move. Diffusion means what? Diffusion means migration of atoms from one location to another location, right? And it should be of sufficient distance, maybe interatomic distance at least. Okay, if the atom is moving at a distance of interatomic distance, that is called diffusion. But less than interatomic distance, it is not basically diffusion. Atoms can move, but if it is less than interatomic distance, then it is not diffusion basically. It is called displacement. We will discuss that. You do understood now? So this structure will break down and finally this structure will come out. So that's why it's called reconstruction. I have very good video on this, you can watch it, I will share it today. Watch it, huh? Then next transformation is called, see, diffusion less. So the name is saying diffusion less means there will be no migration of atoms will take place to a long distance. Neither carbon will migrate, neither iron atom will migrate to a long distance. Long distance means interatomic distance at least. But they will move to a very small distance. That is called shear. Just they will move just a little bit. That is called shear transformation. I have written that. See, some people ask which kind of transformation is called shear transformation. We have called Martensitic transformation is shear transformation. There will be a shear. There will be no diffusion. Neither iron atom will diffuse, neither carbon atom will diffuse. But what will change? Crystal structure will change. Initial crystal structure is FCC, but it will become PCT. Body center tetragonal. Body center tetragonal is close to BCC actually. Close to BCC. But C axis is longer. C by, that's why we have discussed all C by A ratio we need to find out. Higher is the C by A ratio. C by A ratio means this axis should become longer. This is C axis now, and this is the A axis. Okay? You remember the lattice parameters, A's length and angles. Okay, those are lattice parameters. So that means A is one length and C is more length. Right? C by A ratio. That means how C by A ratio is more? Because you just imagine a situation. You have this is one situation, but same is becoming DCT. Why this is happening? Because you are cooling at a very fast rate. You are cooling the steel at a very fast rate. That means you are bringing the steel below A1, but to a very low temperature, but at a suddenly, very quickly. So what it means? That means you don't have sufficient time for migration of iron atom, migration of carbon atom, because they are not getting time. Okay. So in other words, I can say pearlite transformation will happen if you are giving time for transformation, slowly cooling. But if you are cooling very fast, how atom will get time to diffuse or to move? So only option is shear. They will just shear out. You got my point? And if you measure the composition of FCC and BCC, same carbon will be there in FCC and same carbon will be there in BCC. But if you measure the carbon composition in FCC and BCC, will it be same or different? Different. Because more carbon will go and become Fe3C. You got my point? Because this is 6.67 carbon. No? And maximum solubility in BCC is how much? 0.025. Do you got? That means partitioning of carbon is taking place in case of pearlitic transformation. Whatever FCC contain carbon, this will move to Fe3C and some carbon will move to ferrite alpha. But in this case, DCT, all the carbon which is present in the FCC will remain in DCT. Where it will remain mostly in here. See, interstitial site means a small size is there. Carbon is going into the interstitial site. But when lot of carbon will push, so this will become elongated. So C axis will grow. So that's why you find out at the end C by A ratio. C by A. This is one lattice parameter, this is one lattice parameter. So more carbon means more C by A ratio. Less carbon means less C by A ratio. So some people ask, if we have a pure iron, can we make Martensite out of it? Yes, you can do. Even because in some definition they told Martensite is a super saturated solid solution of carbon in iron. Super saturated means lot of carbon is present. Do you got my point? But this term is not always true. You can have a pure iron, you can also have a Martensite. But what is the difference? The strength will be less. Pure carbon Martensite means it is having very low strength because strength is provided by C by A ratio. C by ratio is more means what? More lattice strain is there. Lattice is getting strained, no? Right? More strain in the lattice, more is the hardness, more is the strength. Less is the strain in the lattice. It's the same concept. Like we are forming substitutional solid solution. What we are doing? We are adding lot of alloying element, that is substituting the iron in the lattice point. So if the size of the alloying element is bigger, it will push the iron atom now, of course. So more will be the strain in the lattice. So obviously it leads to solid solution strengthening, substitutional solid solution strengthening. Do you got the point? Similarly, carbon atom is there. Carbon atom is going into the interstitial site and more carbon atom is going. So more will be strain in the lattice, of course. Because space is less, but you are feeding more number of carbon. So it will strain the lattice, of course. So more is the lattice strain, more is the strength, more is the hardness. Do you got the point how Martensite is getting strength? Because of strain in the lattice. I think up to this it is clear. So you can write there will be no migration of carbon, no migration of iron. But here there is complete migration of iron, complete migration of carbon. Diffusion will happen. But this is interesting. See, barytic transformation is mixed kind of. Now can you think mixed means what exactly? Means diffusion will happen and diffusion may not happen. Both are there. Can you just think of it? Which atom will migrate and which atom will not migrate? We have two atoms, now carbon and iron. So just imagine. Iron atom will migrate or not? A diffusion will occur or not? Carbon atom will diffuse because it is small atom, it is lighter. If you remember, I talked about if you take the steel above 200 degree or 250 degree, carbon atom migration will start because it is very light, small, it can move. But iron atom is heavy, na? It needs more high temperature. So simply means this FCC, it has a lattice of iron. So iron sublattice will just shear, but the carbon present in the lattice will just migrate. So you can simply write diffusion of carbon atom will take place during barytic transformation, but diffusion of iron atoms will not occur. Only shearing of the lattice will take place. Do you got the point now? So that's why it is mixed. So we can have mixed transformation, we can have displacive or that is called diffusion less transformation, and we can have diffusion based, complete diffusion will happen. Okay, at least you understood this one, right? And nature already we have discussed, I think. It is very hard and brittle. The nature is hard and brittle. This is very tough, and this is tough and ductile also. Okay, no issue. What else? Okay, this is another important point. So now the question is, you are above A1, or suppose for example you are around 900 degrees centigrade. You are doing austenitizing at 900 degrees centigrade. So now the question will be, at what temperature pearlite will form, at what temperature baryte will form, and at what temperature martensite will form, because different temperature will give you different product. Suppose this is 900 degrees centigrade, your steel is at this temperature 900. Now at what temperature you need to bring the steel so that it will form pearlite at what temperature you need to bring the steel so that it will form benite, and what temperature you need to bring the steel so that it will form martensite. So that is also a very good question. See, perlite transformation occurs in a range. Basically, can you tell me at what temperature the transformation will start? If you are dealing with inflectoid steel, it will be 27 degree or 723. Okay. So most of the people book like 727 basically. This is the start temperature and it will go up to how much? 550. So this is the range of perlite formation. So just understand this. Your steel is at 900 degrees centigrade. Everything is austenite. And the moment you bring the steel just at 727, transformation will start. Perlite will form. It will form. The moment you keep any temperature in between, you will end up with perlite. If you keep the steel at 550 also, you will end up with perlitic structure. But now what is the difference? Suppose you are doing transformation at 727, but and the steel you are doing transformation at 550. So what is the difference? You get perlite, but what is the difference? Size or mostly the interlamellar spacing. That means at 727 you will end up with coarse perlite, but at 550 you will end up with fine perlite. Difference is the interlamellar spacing will be less and more. This is very interesting topic what I am discussing right now. In interview you need to explain like this only. In what condition you need, cooling rate also depends. I will talk about that soon. Yes. It is fine. Now your question is benitic transformation temperature. So just understand, it starts with 550 and it goes up to suppose 250. This is the temperature range of benite formation. Shall I write, or for this it is fine and coarse. Sorry. Okay, anyways. Coarse for this one and fine for this one, for example. It is clear now? Similarly, benite is also two types. I don't know, you have studied in physical material. Upper and lower. Okay, you have studied it. Very good. Upper benite and lower benite. That means you are doing transformation as 250. For example, let me just I am giving an example. You will end up with lower benite. You are doing transformation 550. You will end up with upper benite. Okay. But the point is, benite will form under a condition. It will form under isothermal cooling. What is isothermal cooling means? You need to bring the steel suddenly, like kind of quenching you can say, suddenly to a particular temperature and hold it there. It will cool slowly and it will become benite. That means kind of quenching, but not at very low temperature. But suppose you are bringing the steel like sudden cooling, but you are bringing the steel below 250. So what will happen? Martensite will start forming. Very good. So that means this is very interesting. We have MS temperature and we have MF temperature. This is the range of Martensite formation. MF means Martensite form. Martensite finish, and MS means Martensite start. Okay. So basically this is around below 250. So basically it is around 220 degrees centigrade. And MF you cannot say. It depends upon the composition. Sometimes maybe minus 50, maybe minus 40. See how below you need to go to complete the transformation. So from this concept there is another concept. See, that means basically in real situation we are cooling the steel up to room temperature, or maybe just below the room temperature. Maybe 0 degree you can bring, but below that you cannot do it. It is not practically feasible. You can quench it in the ice, for example, 0 degree, or you can cool it to room temperature 25 degree, but you cannot go to minus 50 or minus 40. So it simply means Martensite transformation will start, but it will not finish. So you can end up with a steel having two phases. One is retained austenite and one is Martensite. Retained austenite means that is not taking part in the transformation. It will remain as austenite phase. Okay? Do you got, or shall I repeat? You know these things. That is good for steel or bad for the property? Retained austenite is good for the property of steel or bad? Huh?
It is good.
Good. It is actually bad. Because everywhere you have Martensite phase, which is very brittle, and you have soft phase. So fracture may start from the soft phase sometimes. But it depends upon the application also and type of steel also. There is a particular kind of steel where you need also austenite phase. I am not going into that, but just understand. Where there is retained austenite, that is a soft region. Failure may start from there. Okay. And there is another kind of Martensite that is called tempered Martensite. I am not going into that right now. You can also write there is a concept called tempered. Tempered Martensite. That is basically nothing but alpha and cementite. Alpha and cementite. Ferrite will be there and cementite will be there. No, I am not going into details right now, but just one line I can say. Tempered Martensite will form by doing one kind of heat treatment. Right? You need to form Martensite first, but Martensite problem is what? It is hard and brittle. Brittle means it is not good actually. It can break, easily break. Hardness may be very high, but it will break. Brittle phase, right? But you need to bring some ductility first. Then only you can put it into application. So that's why we are converting Martensite into tempered Martensite first by doing one heat treatment. Then you can use the steel in some applications. Right? But if you use directly steel having Martensite, it will fail because of brittleness of the brittleness property. Okay, I am not going into details right now, just understand this one. Okay, so up to this it is clear, I guess. Now we'll talk about kinetics. So how fast austenite can become perlite, or how fast austenite can become vanite, or how fast austenite can become martensite, or how slow. We'll discuss that. Just imagine a situation. You have a big piece of steel first. This is a very big piece of steel. You want to do an experiment. What you can do? You cut it into small pieces, very small pieces. This is one, this is two. Fine. You take one piece of steel, you make austenite, that is homogeneous austenite. Then you bring the steel to below A1 or AE1. Achha, what is AE1? AE1 is E for equilibrium actually. Equilibrium temperature. A1 is the lower critical temperature, right? Equilibrium. Just bring the steel to A1. So transformation will start. Actually you need to use a bath, salt bath, and this cooling is isothermal cooling. Let it be, for example, austenite means suppose 900. Let it be 900 degrees centigrade. And this temperature is 727. Okay. And this bath temperature is, for example, let it be any temperature below this. Suppose 700. Up to this it is fine. So you need to hold the sample at 700 degrees and allow it to cool slowly with time. Just give the time. Time is the variable. Temperature you have fixed 700 and allow it to cool. That is called isothermal cooling, basically. So a time will come, perlite will form, right? It will not form directly. It takes time. Similarly, you do another experiment, same experiment, continuously same experiment. But you choose a temperature, suppose 650 now, and cool the sample. You can take a temperature of 600, 550, 500. That means this is for this one, this is for this, third sample is like this, fourth sample is like this, and like this you are doing cooling, right? Each temperature you are holding and allowing the time to cool it. From this, at the end, you will see transformation has happened at individual temperature for given interval of time, and you will get a curve, and that curve is actually IT curve or TTT diagram. We will discuss that now. Is it fine? We will discuss the TTT diagram. The same experiment you can do in lab also if you want. You can ask. See, there is some glitch here. The first, suppose sample 1, you are cooling for a time interval of maybe some second, right? 700 degrees centigrade, but only for second, 1 second for example. From 1 second you take it out and quench it. So if transformation will not happen, austenite is not forming any perlite. So what will happen? Everything will become Martensite. Okay, done. Similarly, you are doing same thing at 650 now, right? You hold it for maybe, okay fine, let it be 700 degrees centigrade. You are holding for maybe 10 seconds now. After 10 seconds, you are again quenching it. So whatever transformation has happened, but rest will be transformed into Martensite, right? Similarly, you are giving some hours, some seconds to hours, but temperature is fixed. Same thing you can do for 650 degrees centigrade, some second, more second, minute, then hours. So whatever transformation not happened, that will become Martensite upon quenching, right? So you will see how much perlite is forming with time, of course. That will tell you the transformation of kinetics. In 1 second, how much perlite has formed? Because more Martensite means less perlite has formed, right? More perlite means less Martensite will form. Okay, do you got the point? So in this way you can do an experiment, and finally you need to draw a plot that we will discuss. See. Okay, so this is your temperature axis and this is your log time. There are two variables. One is the time variable. You can give time for the transformation. You can apply a different temperature for the transformation. Okay. Log T I am taking because log means you can show very small seconds also, fraction of seconds also you can see. You can see some 10 hours, 1 day time also. Very big time you can see, very small time, fraction of seconds also. Otherwise you can write only T if you want to show some minutes or hours. But to show fraction of seconds, you cannot show it in the log book, right? You need log T, that's all. Okay, anyways. And I need what? I need transformation. So first phase will be what? Parent phase, austenite. So I need to draw a line. Okay, and this line will be what? Or A1 or AE1. Above this, austenite will be stable. Below this, austenite will be unstable. Okay, so I can simply write austenite. If you want in details, you can write but condition applied. I am choosing which kind of steel you take it. Don't forget it. Otherwise, if you want to do hyper or hypo, then this is wrong diagram. Listen it carefully. Sometimes they ask this kind of tricky questions. So by chance they ask hypo, then you need to make it A3 or AE3, right? Upper critical temperature, A3 or AE3. Then now just imagine this is how much temperature you remember? 27 degree. And you want to hold at 700. This is 700 for example. Then 650. Then for example 600. Then like this you are choosing different temperature. Okay. The moment you allow the time for the transformation, so the curve will be like this actually. See? So this is the curve finally you will gain. Kind of people call C curve, sigmoidal curve or C curve. Right. Some people call S curve also. It looks like S, that's why this is kind of S, or you can call it C. Right? So now the question is, just imagine you have stable austenite and you are bringing the steel at 700 degree, it will become unstable. So this phase, this part will be what actually? Do you got the point now? See, unstable austenite, you can write also austenite, no issue. Right. But for better clarification, I have written, or you can write supercooled austenite. Supercooled means it will transform, it will not stay. Like people call a supercooled liquid also, like liquid to solid transformation. I don't know you have studied or not, anyways. People call supercooled liquid. That means it can transform anytime, sometimes. Anyways, so this unstable austenite will transform to perlite or benite or martensite. Okay. So suppose at this temperature, this is the start point. Okay, I am using different color then only understand. This is 700, I told for example. This is suppose 650. Let it be 600 around 600. Suppose this is 550. Suppose this is 625. Let it be. And it goes on, right? It goes on. Just see what is this one first line, what is second line. The first line will talk about the transformation has started. That means austenite has started forming perlite or benite or whatever. Martensite will not form right now. We'll talk about only perlite and benite bit better. So that means austenite is stable up to this. See, suppose this is the point. Like I'll draw a projection up to this point. So this is the one time, suppose T2, and this is your T1 time. That means from T1 to T2 time, austenite is still austenite. The transformation has didn't started yet. The moment it will reach this time, transformation will start and it is becoming perlite now. But it will not become finished. It will go on. Why? Because you remember now, transformation of perlite happens due to nucleation and growth. So nucleation will happen, growth will happen, and finally it will complete. So the moment time will go and it will reach at this point, for example, then transformation is finished. So you have to explain the first curve is called transformation start curve and this second curve is called transformation finish curve. Do you got now? You are holding the temperature fixed, that is isothermal I am saying, and you are allowing the time for the transformation. And you will see initially there is no transformation at all. But a time will come, transformation will start, and then a time will come, it will finish. So first C curve is the transformation start curve, second curve is the transformation finish curve. So it means what? Up to this point, austenite will stay, and if you check the microstructure here, for example, what you will see? At the middle portion of this, you have 50% austenite and 50% perlite. Very good. And if you reach to the last, here, then you will end up with perlite. And this point, middle point, 50. And this is some point, maybe some amount. Okay, just start. And if I check, I will tell this point what will happen. 0. There is no perlite at all. Only austenite. Right? This point is 100% austenite. Okay? That's why whenever you choose different temperature and you allow the time, you have a start point and you have an finish point. Start point, finish point. Like this, transformation will go on. But now what is interesting, just see the curve, how the curve is It is C curve, no? So what it signifies? Why it is C? Some interesting point is, let's check. It is C curve. So what it tells? Why the curve is C? Nature she is present. Temperature and undercooling. Okay, time. This diagram is T. You have one time parameter, one temperature parameter, and also transformation parameter. Three things are actually there. I don't know if you have studied or not, maybe. What I am trying to do. I will erase it. As I told, transformation happens because of nucleation stage and growth stage. Nucleation means from parent phase a small product nuclei will form, right? That should be stable also. It should not again decompose into the parent. And growth means that product phase will grow, become bigger, and that is when transformation will complete. So nucleation stage is one when a small nuclei of product phase will form. Growth means that small nuclei will grow into bigger. So two things are there. Now the interesting point is nucleation actually depends, I mean the rate of nucleation depends upon undercooling. It depends upon undercooling. Undercooling is delta T. Okay. So nucleation depends upon delta T. Undercooling. Undercooling means, see, this is the boundary. Listen carefully, this is the boundary. Above that austenite is stable, below that austenite is unstable. So you start at this point, austenitizing temperature, you bring the steel to this temperature. This is the gap, right? So this is nothing but delta T. Okay, you got my point? Or you can say from here to here also, no issue. Because up to this is austenite, so no issue. This gap. Suppose you are doing cooling at this temperature. So that means more undercooling. You are cooling at this temperature, more undercooling. Right? You are holding at this temperature. So undercooling is more. So more you go below the A1 temperature, more is the undercooling. And that undercooling will decide the rate of nucleation. So higher is the undercooling, higher is the rate of nucleation. Okay, is it clear? Higher is the undercooling, higher is the rate of nucleation. Done? But there is a growth mechanism also to do overall transformation. There is a growth mechanism, but growth is something opposite. So growth of the product phase will depend upon temperature. Why? Because growth actually depends upon the diffusion rate. Listen to how I am correlating. You need nucleation and growth. Nucleation rate you understood. Nucleation rate depends upon the undercooling. Higher is the undercooling, higher is the nucleation rate. That is okay, no issue. But when you talk about the growth, so growth rate depends upon the diffusion rate, and diffusion rate depends upon the temperature. Higher is the temperature, higher is the diffusion rate. But lower is the temperature, diffusion rate becomes very slow, sluggish. But a time may come when temperature is very low, there will be no diffusion at all. So that is the reason why Martensite is forming. You got my point? But if temperature is sufficient, perlite may form, benite may form, no issue. Because carbon atom and iron atom can move now. But the moment you bring the steel to very low temperature, there will be no diffusion at all because temperature is not available. Diffusion will not happen. So only product form will be Martensite. Because austenite cannot remain stable. It wants to be transformed to some product. It will transform into Martensite. It cannot stay. Shall I repeat again? Nucleation is one stage, growth is another stage. And if I will multiply this, I am writing N into nucleation and growth, G for example. N is the nucleation rate, G is the growth rate. That is equal to overall transformation. So overall transformation depends upon nucleation rate and growth rate. And what I told, nucleation rate depends upon the undercooling. Right? At what temperature you are holding? If you are holding at a very low temperature, more undercooling, more nucleation rate. Right? But growth rate depends upon the diffusion rate. And diffusion is exponential to the temperature. Higher you go to temperature, it becomes more exponential. More growth will happen or more diffusion will happen, right? But that means, can you tell me, in this diagram, overall transformation is maximum in which temperature? Just see the diagram. At the nose point. This is actually the nose. So at this temperature, this temperature, you have maximum overall transformation happening. Nucleation rate is also good, growth rate is also good. How we can say? Nucleation rate is good means some undercooling you have provided, right? Sufficient undercooling you have provided, nucleation will be better, nucleation rate will be better. And temperature is also sufficient there, so growth will also happen because diffusion is also good, right? So because of this, overall transformation is maximum at the nose point. So it exactly means transformation will start quickly. So this is the temperature where transformation will start quickly. Just see. Why? Because just draw a projection. This is the time gap. Just see, the minimum time in this curve is this much, where the transformation has started. But if you are choosing this temperature, this one, see the gap is more. If you go to this temperature, see the gap is again more. Just opposite. Just see, if I choose the temperature of this one, it become again reduced. If you go more, it become again reduced. Right? So overall transformation is maximum at the nose region. Right? So that's why transformation, that means kinetics is maximum in case of nose point. Kinetics is slow at higher temperature, kinetics is slow at lower temperature, but at the nose temperature, that is 550 degrees centigrade. This temperature is 550 degrees centigrade. Overall transformation is maximum. And there is a question people call, what is incubation period? Incubation period means this gap actually is called incubation period. That means the time interval up to which the transformation will not proceed. Still austenite will be there. Again I am saying, this is the incubation period. Or in other words, what I can say, higher temperature means higher incubation period, lower temperature means higher incubation period. But at the nose point, incubation period is less, very less, minimum. So incubation period means that period of time up to which the transformation will not proceed or not started, you can say, whatever. Is it clear now? People ask what is incubation period in TTT diagram, show it. I think you understood. You can write in the exam. If there is a question, for example, draw TTT diagram and explain what is the initial curve and what is the final curve, what is the C nose point, what is incubation period, right? Why transformation, overall transformation is maximum at the C point, nose of the C curve. You can explain it, right? Okay, very good. Okay, we will not discuss much. I think you understood this one, at least. Asha, do you have any idea about cooling curves? I am asking a question. Cooling curve. In the cooling curve, you don't have idea. No, I am not asking about CCD. I am asking about the cooling curve.
Yes.
Degree of freedom.
To do cooling, we need temperature and time, simply. These are the 2 points, or 2 axes. Suppose I want to cool from this temperature, I can have one cooling curve, this one. I can have another cooling curve, this one. I can have another cooling curve, or maybe I can have another cooling curve. Suppose this is cooling curve 1. Now tell me, in which case the cooling rate is maximum and minimum? C1 is maximum cooling rate, that means very fast cooling, and C4 is very slow cooling. You can imagine this is kind of furnace cooling you can imagine. And you can imagine this one is or rapid cooling, whatever. And these are intermediate cooling. Right? So now tell me in which case perlite will form and in which case martensite will form. In which cooling rate? This one is very fast cooling. That means no diffusion is there because you have bring the steel to so low temperature. Now no diffusion will happen, right? But austenite need to transform because it becomes so unstable now. But you are providing very high undercooling. Nucleation rate is maximum, but growth is not happening. But it need to transform. So martensite will form. So this cooling rate will provide you martensite, and this cooling will give you perlite. This is a diffusion based and this is diffusion less. And in between that, you can have perlite also or mixture of anything. Okay, okay. This is an assignment. Just write one assignment. Draw TTT diagram. Draw TTT diagram. And draw 4 cooling curves. Draw TTT diagram and draw 4 cooling curves. And show 3 products. Show the products. That means each cooling curve will show what kind of product. Cooling curve 1 shows what kind of product. Cooling curve, like I am giving options. One is fine perlite. Just right. Fine perlite is one product. Coarse perlite is one product. Martensite is one product. And benite is another product. Benite will be difficult for you maybe because I didn't discuss about that today. So this is the assignment and maybe you will get same question in exam. Okay, you can end it.